Hello, everyone. This is the fourth in a series of lectures covering Chapter 18. Today, we'll be talking about resonance, which is something I already discussed in the last few sections, but now it'll be condensed into this video for good reference. So as you've seen in the last sections, when you have something like a string on a guitar or an instrument, there's effectively a lot of normal modes that the string holds, and as such can vibrate with any of them, and in such a way that those vibrations generate a standing wave. Now, when you plug them, you actually have this pulse that's created, this sort of superposition of a few different modes, and what you're actually creating is what's called resonance, where the motion that you give to the string, the plucking that you do in the case of a guitar string, for example, basically makes the string vibrate with a bunch of its natural frequencies. And you can also achieve this mechanically by applying a periodic force to the system with a frequency that matches one of the natural frequencies of the system. And this can be done for any medium. So you can generate a standing wave in air as well. So, in like woodwind instruments, in flutes, you can create a standing wave inside the flute by blowing into it. And the reason why these standing waves are important is because they are the loudest components produced by the medium. So when you plug a guitar string, right, what you hear the loudest is the note, which is the standing wave. And in the case, at least of a guitar string, the loudest part of it is this first harmonic, which is why the frequencies of the medium that are the natural frequencies are often called the resonance frequencies, since when the medium is driven at those particular frequencies, it creates a large amplitude, a loud standing wave. So here we just see like a very literal example of that, where we have a motor with a blade attached to a string, and it's driving it at one of the natural frequencies, which again, if you know what medium you're working with, you can determine what the natural frequencies are. In the case of a string, you need to know how long it is, as well as the speed from knowing the tension and the density. So you can then set the frequency to be one of the natural ones, which will create this standing wave, which will be a very, very loud, very, well, in the case of a string, not loud, but large in amplitude, a standing wave through the medium. And what's actually happening, right, despite the fact that it looks like a standing wave, you are sending pulses to the end, right? You're sending pulses towards the right towards the wall in this figure, which creates a series of reflected pulses. So you are continuously sending incident pulses, and there's this continuous stream of reflected pulses, and the overlap is what creates a standing wave. Now, obviously, if you let go, if you separate the motor, if you separate the vibrating blade, eventually standing wave settles down, right, due to damping. But as long as you keep the motor there, then you'll sustain a standing wave. So you can then, right, if you're at the fundamental frequency, then you can keep increasing frequency by integer amounts in the case of a string, and that will take you to another natural frequency. In this figure here, though, you'll note that in the length of the medium, there's about a wavelength and a half, which means that the total wavelength of this standing wave is 2/3 that of the length of the medium, right? Because the length of the medium is from this wall to the start of the blade. And if you see, right, there's like 1/3 here, 1/3 here, and another third from here to here, which means that a full wavelength, right, takes up 2/3. So this is the third harmonic, and thus it has the third longest wavelength of all the harmonics, and the third smallest frequency, since as you go up in harmonics, the wavelength gets shorter, but the frequency gets bigger. And if you don't drive the blade at a natural frequency, then you will not create resonance in the string. You will not get a standing wave pattern, and you'll have a low amplitude, messy wave. That's all for section 18.4. I hope you join me next time, where we'll be talking about standing waves in air quality.